Hello guys, today we continue to study chapter 6 about the magnetism part. First, we learn about a magnet. A magnet is an iron ball magnetized and always has two poles called the North Pole N and the South Pole S. Magnetic poles can interact each other. Like poles repel one another, unlike poles attract one another. In nature, there does not exist monopoles. Magnetic poles always exist in pair. When you divided a magnet into two parts, they become two small magnets. Atoms in a magnet are aligned in the same direction. A force field is a region of altered space around a source. A force field around a mass is called gravitational field. A force field around a charge is called electric field, and a force field around a magnet, a current, or a moving charge is called magnetic field. To visualize a magnetic field, we draw magnetic field lines. That's the imaginary lines. The magnetic field lines around a magnet are like this, from North Pole to South Pole. What produces the magnetic field? To understand this, Oersted did a famous experiment with a compass needle, or small magnet, placed nearby a current-carrying wire or rod. He discovered that the current caused the compass needle to be deflected. This result implies that current produces magnetic field around it. The direction of magnetic field produced by a straight line current can be determined according to a right-hand rule. When you use your right hand to hold the current, let thumb in the current direction, then your four fingers are along the magnetic field direction. Magnetic field is usually denoted by B. It is now known that all magnetic fields originate from moving charges. Magnetic field of a coiled current is similar to that of a magnet. The field strength increases with the number of turns of the coil and the current also. The field direction is determined by the right-hand rule. When you use your right hand to hold the coil along the current direction, then your thumb points to the field direction inside the coil. When an iron core is placed inside the wire coil, the magnetic field is enormously enhanced. A wire coil with an iron core is usually called by electromagnet. Magnetic field can exert force on current. When you place a current in a magnetic field, the field can exert force on the current. The direction of the force on the current by the field can be determined according to the right-hand rule. The right figure shows that an inward magnetic field exerts a leftward force on an upward current. Current produces magnetic field, and the magnetic field exerts force on current. Therefore, currents can exert magnetic force on each other. Currents attract each other if they are in the same direction, and repel each other if they are in the opposite direction. Electric motor is a machine that uses magnetic force to turn a current-carrying wire loop to prevent the loop from stop or not rotating in the back and forth manner. An electric motor usually uses a commutator that changes the current direction, or uses alternating current that changes direction itself. We don't go into detail about the design of the electric motor. That's the physics. So electric motor use the magnetic force to turn the current loop. Section 18 about the electromagnetic induction. Faraday experimentally discovered that when a wire is moving across a magnetic field, an electric current is induced in the wire. The direction of the induced current is in the direction so that the current The direction of the induced current is in the direction so that the current or wire is forced by the magnetic field in the opposite direction of the motion. The strength of the induced current depends on the length of the wire, the speed of the motion, and the strength of the magnetic field. Electric current can be categorized into two types according to whether they change direction or not. Direct current and alternating current. Direct current can flow in one direction. Direct current that flows in one direction, DC. Alternating current that flows in the back and forth manner. So sometimes this direction and reverse the direction. Yeah. An important application of electromagnetic induction is the transformer. It is a device that consists of two coils with a soft iron core. A transformer can change the voltage of alternating electricity. Also the current. The ratios of voltages and currents between the primary coil and the secondary coils are determined by the ratio of the number of the turns in the coils. The two fundamental formulas for a transformer are the ratio of voltage V1 over V2 equal to the ratio of number of turns N1 and 2. The ratio of current is the reciprocal of the ratio of voltage or the ratio of number of terms. So I1 over I2 equal N2 over N1. Multiplying these two formula, these two the ratio, the voltage ratio to the current ratio, multiplied together, we have the conservation of electric power. I1 V1 equal I2 V2, the P1. I times V, that's P, so P1 equal P2. That means a transformer does not change the electric power. Transformer only changes the voltage and current, but not power. Of course, this is talk about the ideal transformer. Here is an example about a computer adapter, which is a transformer. To find the current and the number of terms in the secondary coil, N2 and I2, when the voltage, current, and the number of terms in the primary coil and the voltage of the secondary coil are all given. So V1 equal 120 volt, I1 equal 2 ampere, N1 equal 100, and V2 equal 12 volt, and find N2 and I2. From the voltage ratio formula, V1 over V2 equal N1 over N2, we have N2 equal N1 times V2 over V1 equal 100 times 12 divided by 120 equal 10. So N2 equal 10. From the current ratio formula, I1 over I2 equal N2 over M1, we have the current in the secondary coil. I2 equal I1 times M1 divided by N2 equals 2 times 100 divided by 10 equal 20 ampere. So N2 is 10, I2 is 20 ampere. That's the end of this chapter. Thank you.